everyone, my name is Hannah and welcome to today's General Maths Units 3 and 4 lecture. So ATAR Notes has been around since about 2007 and we've been offering these free lectures since 2015, and they're just one of the resources that we offer to help students as much as we possibly can with their studies. If you are looking for any other really cool free resources, we've got a whole bunch. If you want to go to our website, you can check them out. There's articles, free study notes you can download, more lectures just like these ones. So if you are looking for some more of those resources, please do feel free to check those out. And then we also do have our range of paid resources as well. So that's including like our study note summaries, like those books that we've published, as well as like the question guides. We're bringing out flashcards, course videos, there's text guides, and there's even an AI answer bot, which is really, really cool. And yeah, if you want to check out those, please feel free to go to ATAR Notes Plus. All of those are really helpful, really concise, and yeah, really can help you with those practice questions, content summaries, and all of that kind of thing. But yeah, without further ado, let's get into today's lecture. So as I said, my name is Hannah and today is the April lecture for General Maths Units 3 and 4. And today we'll be focusing mainly on some Unit 3 revision. So hopefully going over some of the trickier topics, drawing your attention to some tips and tricks, and making connections between the content and hopefully consolidating what you've already gone through in class. So just a little bit more about me. I graduated in 2021, so a few years ago now, and I studied biology, psychology, English, general maths, drama, and outdoor sport and rec. So I had a really good variety of subjects and I really enjoyed all of them. And I actually got a 99 out of 100 for general maths, which I was very excited about. So hopefully I'll be able to pass on some of the tips and tricks and knowledge that I found really helpful to help me do really well when I did this course myself. And currently I'm studying a Bachelor of Education, Primary and Secondary, majoring in biology. So that's, what I'm up to at the moment. I really enjoy teaching, so I love that I get to do that through work at ATAR Notes at the moment as well. So yeah, if you do have any questions about uni, the content that we go through today, anything along those lines, please feel free to put it in the live chat box. And yeah, I'd love to help you out with anything else I can along the way. So that's a little bit about me. And a quick overview of what we're going to be going through today. Like I said, mainly a Unit 3 revision session. We'll start with a fairly brief overview of bivariate data. We'll go through a bit of time series, sequences, earth geometry, and then if we have time in the end, tips and tricks. And again, if we don't quite make it through all of the content today, you'll be able to download the PowerPoint slides from this page here, so make sure you go check those out. And also, if you want to come back to anything as well, you'll be able to rewatch the lecture from this page as well. And again, please feel free to make the most of the live chat and we'll answer all your questions there. Another quick thing I want to flag before we fully get into it is that as this is only a 2-hour lecture, we definitely won't be able to cover all of the content from Unit 3. That's quite a lot of depth and breadth, and we won't quite be able to go into as much detail as I'd love to. So my first tip for today is to just make sure that you're continually referring back to the syllabus to make sure that you are hitting all of the points that you need to. So if at any point you're not sure what exactly you kind of might need to go into a bit more depth with, or what could be assessed on either your internal assessments or your external exam, make sure you keep referring back to the syllabus, which I've linked in the slides. So definitely get super familiar with that. And again, my kind of approach for today is I want to kind of try and help you make as many connections between different content as possible, because that active learning is really helpful in improving recall. So as you're watching, I'd love you to be as actively engaged as possible, whether that's like chucking questions in the live chat. If we have a practice question, you're more than welcome to try and work it out as we go, or pause the video to engage with that. Or making those connections between content as well for yourself. So whatever works best for you, and note taking, whatever that might look like, I'd really encourage you to engage as actively as possible to really make the most out of today's session. So bivariate data, let's get into it. Topic 1 of Unit 3. It might have been a little while since you've covered this, so it could be some good time for revision. So bivariate data. Bi is the prefix meaning two. So we're looking at data with two variables. And the way I like to remember that is like bicycle, bivariate, prefix bi means 2. So that's a little trick that I like to use as well. And because we have these 2 different variables that we're looking at, which we don't have when we were only looking at univariate data in year 11, units 1 and 2. But now that we do have bivariate data, and we're looking at data that concerns 2 separate variables, we're looking for meaningful ways to represent this data so that then we can analyze it and see if there's any like patterns and relationships that we can find. So this might kind of start to be like ringing some bells to what you've gone through in class. So we're thinking maybe, for example, two-way frequency tables, scatter plots. These are some of the different ways that we look at to represent the data so that we can then conduct further analysis so that we can then extract meaning from it. Because just a table of like survey answers or a table of number data, like it's not always like the most helpful form to extract meaning from. So that's really what we're doing with the bivariate data. We're putting it into a form that's helpful, where we can visually break it down or use other techniques so that we can really draw meaning from it and see, is there a pattern or a relationship here that we could discuss? So there's some more terms that you likely be familiar as well. We can have categorical data, numerical data, and when we have bivariate data, so those 2 variables, we can often identify the explanatory variable and the response variable. Have a think back to see if you remember what each of those terms mean. But just in case, we'll quickly go over those now. So the explanatory variable may explain the associated change in the response variable. It's important to have this kind of foundational definition so that we know that we're on the same page when we're talking about these things. So as an example, I'd like you to have a think about, so if we were talking about the age and price of a car, which would be the response variable? It would be the price, because when we're thinking logically about this, the age of the car may explain the associated changes in the response variable. But because this is only like observational like data, we can only draw conclusions about like association and correlation. We can't actually talk about causation. So that's why we're kind of just predicting and making guesses about which variable we think may be causing the change in the other. So in this case, we'd say the explanatory variable would be the age, because we think that might be the factor that's driving the associated change in the response variable, which would be the price of a car, which makes sense because there's a pretty clear trend there when it comes to how old a car is and how expensive it might be for a number of reasons. So categorical variables are categories: small, medium, large, yellow, blue, Toyota, all these different categories that we can look at. Whereas our numerical variables are our numbers. So that's our continuous data. So it's things that we like count, measure, record, all of that. It could be centimeters, degrees Celsius, all different types of numerical data we can have. So bringing it back again to what I was talking about earlier with how do we represent our different types of data. So how do we represent categorical data? We represent it in a 2-way frequency table. So we have an example of one of these here. One thing that I want to draw your attention to as well is the word 2 in the title, 2-way frequency table. That's actually not referring to the fact of like how many columns or how many rows there are. We could actually have multiple columns or multiple rows and still have it be called a 2-way frequency table. It's a 2-way frequency table because it goes 2 ways. We can kind of read down and across it both ways, and by doing that we can actually draw meaningful results. So like I said earlier, instead of just having a whole list of this year 11 voted yes, this year 11 voted no, this year 12 voted yes, like that actually doesn't help us be able to interpret the data. But when we tally it up and put it in a 2-way frequency table, we're then actually able to draw meaningful relationships from that, because now we can interpret it now that it's in this much easier form. And just like what I was saying, like there actually does seem to be an association. So let's say, for example, this data is about whether year 11 or 12s are for or against phone use at school. So here we could see that 36% of year 11s are for phone use at school, while 64% are against it. And even there, by using that language intentionally, even just by using that adjoining word while, I'm really intentionally comparing them and like contrasting and discussing the difference between it and drawing a conclusion from that, which would be that if we're looking at year 11s seem more likely to be against phone use at school. Whereas, another connecting word you can use if you're asked to discuss a two-way frequency table, whereas, so I'm pointing out that there's actually a difference here. In year 12s, we actually see the opposite thing. It would be more like 81% of year 12s are for phone use. So we can already start to see a really strong pattern emerging there. Another quick thing I want to draw your attention to is the fact that this two-way frequency table has already been converted to percentages for the columns, whereas in a two-way frequency table you often might see the individual number of votes in like each column, and then you'll have the raw total number here, and then also the totals here and here. But what they've done to this two-way frequency table is they've actually converted it to percentages so that we can compare our value on equal footings. Because if we had interviewed a different number of year 11s and 12s, then it wouldn't be it wouldn't be fair to compare the raw numbers, but by converting it to percentages, we can compare it on equal footing. So that's important to note as well. Another quick hint, if you do struggle with, because it can be quite a tricky thing, with drawing conclusions from two-way frequency tables and figuring out how to kind of communicate that in an exam, for example, teal or peel or a similar paragraph structure along those forms can be a really helpful scaffolding guide. And again, that's not like a rigid, you must include each of these elements, but for myself personally, that really helped me remember each of the important elements I'd have to include in my answer if I was asked to draw a conclusion about a two-way frequency table. So for example, just to break it down a bit further, it would be topic sentence, evidence, explain, linking sentence. The main kind of takeaway from that is you need to make sure you're stating your point really clearly. You're not just restating numbers from the table. You're not just saying 36% of year 11 students. That's actually not drawing a conclusion. You actually want to draw that information out further. You want to make a point that's explicitly responding to whatever the question is asking you. And then you need to take that evidence from the table to back it up so that your marker knows that you do understand what's going on in the table. And then you make a point about it, elaborate if you need to, and then link it back to the question if you need to as well. So that's just one little quick helpful guide. But yeah, I think could possibly help some people if you're looking for a bit of a structure to help you when writing reports about two-way frequency tables. Whereas when we have numerical data, we actually represent it in a scatter plot. We actually don't use a two-way frequency table. One thing that I find quite interesting when we're thinking about just why we use it for either, imagine if we were going to have a two-way frequency table for a numerical variable, example, temperature. So I said earlier that we actually could have multiple columns, but imagine how many columns we'd need if this top variable was temperature. We'd need like 10.1, 10.2, 10.3, 37.54, 38.97. We could just end up with an almost infinite amount of columns because of the very nature of the data, because numerical data is continuous. So it actually doesn't make sense. It's not practical to record it in a two-way frequency table. Whereas when we look at a scatter plot, we can see we have a nice continuum here from 0 to 25. So no matter what my numerical variable is, I can actually just go along my axis and then plot the corresponding point. So that's why scatter plot just logistically makes so much more sense for our numerical data. So how do we visually represent numerical data? Like we said, we do it in a scatter plot. And the awesome thing about scatter plots is it's actually even easier to see our patterns and relationships than in our categorical data, which is represented in our two-way frequency tables. So we can actually visually see it. And when we have this type of data, you'll probably be familiar with these terms as well. The kind of things we discuss is the strength, direction, form. And I want you to have a quick think now about what those terms might refer to. See if you can recall that in your mind. So here's another example of a scatter plot. This is exploring the correlation between the kilometers traveled by 2012 Toyota Corollas and the price of a bunch of 2012 Toyota Corollas. So let's have a look at the different things we talk about. First, direction. So you might have been able to recall that when we're talking about the direction, we're talking about kind of the overall trend or direction of the scatter plot. So it could be positive, it could be negative, or no association. So if it's positive, as our explanatory variable increases. And remember, our explanatory variable, we always plot on the bottom, just like in science, we plot the independent variable along the bottom, and then we plot our response variable along the y-axis up here. So if we had a positive direction, as our response variable increased, as our explanatory variable increased, so too would our response variable. But that's not what we have here. We can actually read on our scatter plot really visually that as we progress further right on the graph, as our explanatory variable increases, our response variable is actually decreasing. So we have that inverse relationship. We can really see that negative pattern just quite visually on our graph. So direction is the first thing we discuss. And then also form. So form being like linear or non-linear. This one, I would say it looks pretty linear to me. Next thing is strength. Is it strong? Is it moderate? Is it weak? Well, for this particular scatter plot, the dots are like fairly closely clustered together, so I'd probably guess somewhere between like moderate to strong. Like it's seeming like a pretty well-established relationship. Like the dots just aren't randomly scattered around. And then the last thing is outliers, which I wouldn't say we really have any significant outliers here. They're all kind of fitting our trend or pattern pretty well. So to kind of pause there for a second and make some links to our other content. For all of these, I've just assumed, I've guessed that it's linear. I've assumed that it's negative, and I've kind of vaguely guessed that it's strong and moderate. But what I kind of want to challenge you to think about is there more precise mathematical ways that we could kind of discern each of these? And yes, there is. So it might have potentially come to mind with the direction when we calculate an R value. An R value, a Pearson's correlation coefficient, is actually positive or negative, and the sign actually tells us about the direction. So this, for example, because it does appear to be quite negative, I would assume that it's going to have a negative R value, and that could actually confirm for me that it is a negative relationship. Or to link this in with a least squares regression line, if it has a negative slope or a negative gradient, which this definitely indeed would if we were to add a least squares regression line, the signs, whether it's positive or negative, of the slope would also tell us that information. And what about the form? I've just assumed this is a linear relationship, but if I wanted to test that mathematically, I'd have to calculate, you might have guessed it, a residual plot. Because remember, our residual plots test the assumption of linearity. So at the moment, I've just assumed it. But if I want to prove it, I would need to construct a residual plot. And then when it comes to the strength, we touched on it briefly before. Again, that's our R value, our Pearson's correlation coefficient. Whereas here, I'm just saying like, maybe it's like moderate to strong. If I calculate a Pearson's correlation coefficient, I can determine exactly mathematically and precisely what is the strength of this relationship. And again, R value is only appropriate if it is linear data, and because this does appear linear, I would definitely be able to calculate a Pearson's correlation coefficient. Well, only definitely if I'd first also constructed a residual plot to prove that it was linear, and then I'd be able to calculate my R value to kind of determine that mathematical strength. So there's some interesting connections for you as well. So moving on to what we just mentioned, our R value, our Pearson's correlation coefficient. So this measures the strength of a linear relationship. And also it does tell us about the direction. So instead of, maybe weak, maybe no association, maybe moderate, maybe strong, we actually get that exact precise mathematical number value that tells us about it. And like I said before, we generally assume a linear relationship is present, but in some cases it isn't. And a residual plot is how we can kind of figure that out, so making that connection again. And when we're calculating R values, we usually do use a calculator to do it because it is quite a painful process by hand. But there are little tricks and strategies you can use to kind of speed up that process if you do need to calculate it by hand, but we won't be going into that today, just for the sake of time. Another handy hint that I have for you guys is to get familiar with your formula sheet. I cannot emphasize that enough. It is so important to know what formulas are on your formula sheet. So first, you know which formulas you're going to have access to in the exam. Second of all, so that you know which formulas you're not going to have access to in the exam, so you know you need to memorize, and finally, so that you know like what version or form of the formula you're going to have access to. Because sometimes we can learn a few different formulas, and it's really, really important to know which one you're going to have on your formula sheet so that you can then make the decision like, oh, I actually don't like that version of the formula, so I'm going to memorize this one because I think that'll be most helpful for me. Or you can go, no, I just want to use the formula on the formula sheet. So you need to make sure you know what the variables mean and represent. Because if you don't know what I or R or T in a certain formula represent, then it's not actually a very helpful formula. So the more familiar you are with the formula sheet, the more helpful it will be come exam time. So Pearson's correlation coefficient is a number between -1 and 1. So we talked about before how the sign before it indicates whether it's positive or negative, which is again our direction. So is it a positive or is it a negative? So our negative R values are between 0 and -1. And then our positive R values are between 0 and +1, the opposite. And then the size of the number, so the size of the R value, again tells us about the strength of the association. And this is an example of like a classification system that you could use to help work that out. So for example, the ones that are closer to 0 is what we call like a no association. So as a general rule, the closer it is to -1 or +1, the stronger the relationship, and the closer it is to 0, the weaker the relationship it is. I'm going to illustrate that a bit clearer on our next slide. And again, just to further flag that warning there, we can only calculate R values for linear data sets. Because if it's a non-linear data set, for example, like a parabola or like an exponential curve, then R value isn't helpful because Pearson's correlation coefficients are only for our linear data, which is why it's important to do a residual plot if you're unsure. But to come back to what I was just saying about before, this table actually illustrates it quite well. So you can see that if our R value is kind of hanging around that 0 mark, our points are really loosely associated. There's just no association going on. They're kind of just randomly scattered around. But you can see that the closer we get to 1, the stronger our relationship is getting, and the closer we get to -1, the stronger our relationship is getting, just it's a negative relationship. Whereas the closer we get to +1, the more strong positive relationship it is. So having a bit of a rough kind of guide for like these kind of classifications in the back of your head is super, super, super helpful and important. Because you might be asked to like interpret what does a R value of 0.84 mean, and then from that you can actually interpret that with 0.84, it's positive, so I know it's going to be a positive relationship, and if it's 0.84, I know it's going to be quite strong, so I know that it's going to be strong. And then you can also infer from that that it's going to be a linear relationship, otherwise it wouldn't have been appropriate to calculate an R value in the first place. So you can learn a lot from both scatter plots and R values, no matter which one you have first. This is just like another little helpful guide to help you with like interpreting the R value. If you find that interesting, pause and have a look at that there. And this is one of my favorite handy tricks of all, which is how to actually calculate the Pearson's correlation coefficient using your calculator. So you need a scientific calculator to do this, and it's as simple as following through each of these steps, which again, you can download the slides or take a screenshot if you want to save this for later. So the first thing you do is you press the mode button on your scientific calculator. It might be next to the on button, or it might be somewhere else depending on your calculator. And then it'll bring up some options, and you want to choose, you want to press 2, which will say stat. It'll correspond with the word stat, which is short for statistics. So this is to symbolize that you're putting your calculator into statistics mode. And then you'll press 2, which will say A plus BX, which is referring to bivariate data. You can see we've got our 2 variables there. And then it'll bring up a little table on your calculator screen. And then so you enter your data values. So if, for example, your X value is 5, you'd put 5, enter, and that would add it to your table. You can enter all your X values and all your Y values by putting the number in, then pressing enter. And then also by moving around the little table grid using like the arrow keys on your calculator. So you enter all your data that way, and once you've entered all your data and you've finished, then you press on, and that will actually clear your data off the screen. But don't stress, your calculator has it stored in its memory. It's not gone. And then after that, you press Shift, 1, 5, and 5 will be associated with, it'll say REG, which is short for regression, which is what we're doing. We're doing regression data analysis. And then you press 3, which will correspond with R. And then once you hit enter, that will actually give you your R value. And if anything like this doesn't quite line up along the way, go back, give it another try. And again, remember your R value should always be between -1 and 1, because that's the only possible outcome for an R value. And then this step's really important at the end to put your calculator back into regular mode, so it's not like interfering with your calculations, because like the settings can get a bit weird sometimes. Make sure you again press mode and then 1 to get it back to that regular settings. So coefficient of determination, you might remember as well, is quite heavily connected to our R value, because the coefficient of determination is R squared, and how you calculate it is literally R squared. So once you have your correlation coefficient, you can actually take that number, you square it, and that gives you your coefficient of determination. And a word of warning here is no matter whether your R value is positive or negative, once you square it, it will always come out positive. Because if, for example, your R value is -0.7, to square it, you times -0.7 by -0.7. And we know that when we multiply a negative by a negative, that gives us a positive. So our coefficient of determination actually doesn't tell us whether our direction is positive or negative. We need to go back to our R value, our scatter plot, to figure that out, because a coefficient of determination will always come out positive. So a quick refresher, what actually is a coefficient of determination? It's the percent of the variation in the response variable explained by the variation in the explanatory variable. So coming back to my example earlier with like the car and like the kilometers traveled and the cost, if, for example, my coefficient of determination was, let's say, if, for example, it was 0.7, that would mean that 70% of the variation in the price of the car is explained by the variation in the kilometers traveled by the car. And that would imply that 30% of the variation in the price is accounted for by other factors. Again, because we're doing that bivariate data analysis, we're looking at the relationship between those two variables. We need to keep in mind that there are other factors that are also influencing that same response variable. So we can learn that from our coefficient of determination, which brings us to our next bit, which is our least squares regression line, which is pretty much a mathematically exact line of best fit. It's not just roughly drawing in a trend line, it's exactly figuring out what line best represents the overall pattern of my data. And the reason how it technically does that is by minimizing like the sum of like the residuals, which is really interesting. But again, won't be going into that today. And it's usually in the format of y equals bx plus a, where y is our response variable, b is like the slope or the gradient, x is the explanatory variable, and a is the y-intercept. If you've ever wondered like what the y-intercept means, it's like literally referring to the y-intercept. So if we extended this trend line, the y-intercept is where this line would intercept the y-axis. And because of that, mathematically, whatever our y-intercept is, it's always, always, always when x equals 0. So if you ever need to find the y-intercept, and you know, like if you have values for y and x that you could use, you can just say let x equal 0, and that'll tell you what your predicted y value would be for when x is 0, which would give you your y-intercept value. So that's really important to keep in mind. Or if you know, if you know any 3 of these points, you can actually mathematically figure out the last, just like with any formula. So that's a quick overview of our least squares regression line. And because we have this least squares regression line, or this trend line, we can actually use that to make predictions by substitution. So if, for example, you know the y-intercept and you know the slope, and you want to know what y is, for example, when x is 4, you can really just sub that straight into the equation. So let x equals 4, solve the equation and see what y would be, which would be this point about here on the line. So it would probably be something in the low 20s. That also kind of brings to an interesting distinction between interpolation and extrapolation. So have a think about if you remember the difference between those two. So interpolation is when we're making predictions within the given data set, within the range of values that we know, but extrapolation is when we're making predictions that go beyond the data that we have. And as a general rule, something really important to remember is that interpolation is always more reliable than extrapolation. Because interpolation, we've got this data, we've calculated this trend line based off this data, but the danger is with extrapolation is we actually have like no way to know whether this pattern like continues on beyond the research that we've done, because most linear patterns don't go on for forever. For example, with my car example from earlier, if that linear line pattern kept going, eventually a car that had driven a certain amount of kilometers would be free or even like $, which just doesn't make sense. So that's the danger of extrapolation. It can kind of like give us values that just aren't reasonable or possibly aren't even possible. So that's the danger with extrapolation. And also have a go at see if you can identify where the residuals are on this graph. Our residuals are these distances here. So the residual is the vertical distance between the actual data point and its predicted value from the line of best fit. So this would be our residual value here for this point here. So linking it back in again to what we were saying earlier about our R value, with our R value, we were saying that it's only appropriate to use a Pearson's correlation coefficient if it's linear, but it's also only appropriate to use a linear trend line if it's got a linear relationship present. So how do we know if a linear relationship is present? And like I alluded to earlier, it is with residual plots. So that's how we determine whether a linear relationship is present or not. So a residual plot might look something like one of these. So how do we actually interpret a residual plot? And again, they exist to test the assumption of linearity. So if we're constructing a residual plot, our goal is to figure out if a linear relationship is present. The most important thing to remember, or like the handiest way that it kind of sticks in my brain how I remember it, is if it's non-random, then it's non-linear. But if it's linear, the points will be randomly scattered above and below the line. So I'll show you what I mean here. So here, our data points are not random. There's actually like a pattern going on there. And that's kind of like the goal of a residual plot. It kind of zooms in to see if there's any underlying trends or patterns that we kind of couldn't see in the original scatter plot. And that's what's happened here. We've plotted all our values on the residual plot, and I won't go into now how to calculate the residuals and all of that. That's something you could do some practice questions on a little bit later if you'd like to rehearse that knowledge. But because we can see here, our points aren't randomly scattered. There's actually a really clear pattern going on here. That's what I meant earlier about how non-random means non-linear. So if I come back to our next slide again, this is non-random. Therefore, from this residual plot, I would conclude that this relationship is non-linear. Whereas this one, we can see that our residual points are randomly scattered above and below the line. So it's super random. So this tells me that there is a linear relationship present. So when interpreting residual plots, non-random means non-linear, and randomly scattered around, yes, it is linear. So that's just a little clarification on residual plots. And again, least squares regression lines. You can also calculate the A and B values using your calculator. It's almost the exact same process as doing it with your R value. I've got the steps up on the screen here. It's mode 2, enter your values, press on, shift 1, 5. Then you press 1, which will correspond to A if you're wanting to find out the A value, which is the y-intercept, or you press 2 if you're wanting to find out B. which is your gradient or your slope. And another word of caution here is it's important to make sure that you've got your x, what you've classed as your x values consistent and your y values consistent. Because if you flipped your x and your y values, you would get different variables. So that's why it's important to identify what's your explanatory variable and what's your response variable right at the start. And like I touched on earlier, association does not mean causation. When we're talking about scatter plots, we're talking about correlations, we're talking about associations, but we cannot discern causation from that. There's lots of different things it could be. It could be the common response, confounding variables, or sometimes a coincidence. So that's just another word of caution there. Whenever we're talking about all of this, we're talking about association and correlation, not causation, because there could always be kind of underlying factors or other variables that are kind of influencing our data that might not be obvious at first. So a quick overview to sum up what we just talked about with our scatter plots and everything, which is actually called like a regression analysis. You can kind of see like the awesome kind of like overarching pattern of like why we kind of do each step. So we start out with like, we construct the scatter plot to see if like visually, like can we actually identify, is there an association or a pattern present? And then we can calculate an R value to kind of get that precise strength of the relationship. And that also tells us about the direction. And then from there, we can like calculate a least squares regression line. We can plot that on our scatter plot. We can interpret the y-intercept and the slope to see like what actually is going on here. We can learn more by calculating a coefficient of determination, which we talk about that in terms of like the predictive power. We can use our least squares regression line to make predictions. Sorry, not using the residual line, using the least squares regression line, we can make predictions. We can also do a residual plot to test the assumption of linearity. We can write a report to communicate our findings. We can answer questions about it. And then this would be a little bit different for categorical data. Have a think about how our process differed for when we were interpreting categorical data. So that's kind of the 1,000-foot overview of what we just went over, bringing it all together. I hope this is helpful, kind of gives you like a bit of an idea in your mind of all the different little things that we've just gone over. That kind of puts them in context a little bit. So awesome, topic 1 is done. We've covered a lot of content there, so hopefully that was a helpful overview for you. If you do need to take a breather at any point, please feel free to pause the video. But for now, we will be moving on to topic 2, which is time series analysis. And the awesome news that I have for you guys is that time series analysis, topic 2, is actually a lot smaller than topic 1. There's still some challenging concepts in there that can take you a little while to wrap your head around. But for a lot of it, it is actually quite similar to our topic 1, our bivariate data. And you can probably start to see a lot of that similarity right here as well, because our time series plots, which is what we call these, where we plot our time series data, are actually quite similar to our scatter plots, with one of the main distinctions being that when we're doing time series analysis, our explanatory variable is always a measure of time. So whether that be seconds, months, weeks, minutes, even decades, just some sort of measure of time. And then because our explanatory variable, which we always plot down the bottom, is some sort of measure of time, then whatever our response variable is, what we're looking at how something changes in response to passing time, that's why our other variable in this case is always going to be the response variable, because the thing that is driving the change in time series analysis is always time. So that's why time is our explanatory variable. And then whatever our other variable is the response variable. And then also we actually connect the dots, whereas we don't do that in a scatter plot, and it would make our scatter plot quite messy. But because with time series analysis, we only usually have like that one data point, that one recording for each time point. And because time is like a continual, precise, linear, and unchanging relationship, that's actually why we can connect the dots. So it's quite similar to a scatter plot. We've got our explanatory variable down the bottom, always going to be time, our response variable on our y-axis, and then we just plot our points like normal. We connect them. We can even add a least squares regression line. So there's a lot of similarities there, which is quite helpful. And there's another example of a time series plot just there. So again, a time series plot is a representation of time series data, which is just when a variable is recorded at successive time intervals. So we're always interested in how our response variable is changing over time. So for example, think about temperature. We could map how temperature changes throughout the year, or we could map how ice cream sales change throughout a week, or throughout a day, or throughout a year. And then think about the patterns that we might see because of that. So again, making that really active link. We're always looking for those patterns and relationships. We're always looking for how can I draw meaning from this data? We're not just interested in putting it on a scatter plot or a time series plot to make it look really pretty. We're actually looking for how can we draw meaningful conclusions? How can we interpret patterns and relationships to learn more about whatever it is that we're looking at? So again, we're looking for certain features. So to kind of make that connection again, in scatter plots, we were looking for, do you remember the 3 categories? It was the direction, strength, and form. When we're discussing time series plots, we're looking for different features. And the syllabus, which again I've linked here, tells us what features we're looking for. So here we can see that under our first kind of sub point of the time series analysis, you need to be able to construct time series plots. So by breaking down kind of the key features of a time series plots, hopefully you're already feeling a little bit more equipped to do that, and practice helps with that a lot as well. And then the second point is that you actually need to be able to describe time series plots by identifying features such as trend, which the syllabus defines as like long-term direction, so that overarching like pattern. Seasonality, which is systematic calendar-related movements, talks about irregular fluctuations and also outliers. So you can kind of see all of the different terminology that if in an exam question you were asked to discuss a time series plots, this is the different language that they're really expecting you to be able to bring in. And this, again, if you want to take a screenshot or download the slides, is just a really helpful kind of condensed kind of summary of what each of these are. So again, trends are our overarching patterns. It's the tendency for our values to generally increase or decrease over a significant period of time. If you are asked to kind of analyze or make a statement about a time series plot, trends are always a really good one to discuss because most time series plots do have some sort of trend. And depending on what our response variable is, will depend on what our conclusion is about what's happening over time. Our second one is seasonality. So when we're talking about seasonality, we're thinking calendar patterns. So it might just, the first thing that springs to mind with seasonality might be summer, autumn, winter, spring. And that's totally okay if it is, because that's still what pops into my mind straight away. But the important thing to keep in mind is that seasonality, it's actually not just about those 4 breakdowns of the year. A season can actually be any calendar related like period or breakdown of time. So a season could be a week, for example, because there are 52 weeks in a year. A season could be a day because there's 365 days in a year. Or a season could be a 3-month stretch, like how we typically understand seasons to represent. So again, seasons are our calendar patterns. So they're our predictable calendar patterns. They're usually pretty predictable, and we're normally talking a year or less. Whereas cycles, our next kind of terminology, is more those longer term patterns, so usually greater than a year. So for example, if we were looking at like certain trends or patterns over like decades, we're more looking at cycles than seasonality. So that's just that distinction there. And if we have a structural change, this is actually an example of a structural change here because we had an established like trend or pattern in our time series plot, and then we had a structural change around time point 13, and that actually resulted in a new trend or pattern being formed. And so that's kind of what we're talking about when we're talking about a structural change, and that could often be like reflected or explained by like external events. Next one, outliers, probably pretty familiar with. It's just a single unexplainable point that stands out from the rest of your data. And just to kind of make that point clearer, if you follow like my laser pointer, so our structural change example we looked at was when we had a continued pattern, and then we had a structural change, and then we had a new pattern. But if, for example, we had an outlier, it would kind of be we're following with our pattern, we've got one outlier, but then we go back to our regular pattern. That's kind of our difference between our structural change and our outliers. And then lastly is irregular fluctuations, which is essentially everything else, all things unpredictable, unexplainable, and present in any real-world data. So I know that's a lot to think about, and you might be able to come up with some helpful like mnemonic or something to help you remember each of the things you might be able to discuss in a time series plot. And sometimes it can just take a bit of practice to kind of get a bit better at identifying these things when you do see them in a time series plot. So yeah, that's a lot of different things we can talk about. So when we're looking at a time series plot, you've already got all of these different things going on in your mind, but we're going to bring in another factor now. So bringing it all together a little bit. Hear me out. So what if we wanted to remove the impact of irregular fluctuations, or if we wanted to remove the impact of seasonality to try and see, is there actually an underlying pattern that's being obscured by these things? And we can. So that's actually how we link in smoothing and deseasonalizing data. So again, I'm trying to help you make these connections. So when we're talking about irregular fluctuations, we're talking about kind of those random ups and downs that might kind of obscure the underlying relationship. And so it can actually make what's actually going on really hard to see because it's kind of like obscuring it. It looks really messy up and down. But if we apply smoothing, we can actually remove the effects of that and kind of look for those underlying patterns and trends. And then same, if we have seasonality present in our data, by deseasonalizing it, we can actually remove the impact of seasonality so that we can see if we put the impact of seasonality aside, do we actually have any trends or patterns there. So smoothing, we have the 3 moving average and the 5 moving average, also kind of referred to as the 3 moving mean or the 5 moving mean. Probably familiar with those terms. And we can also do the 2 moving mean and the 4 moving mean, but when we do it that way, we need it with centering, which we won't be going into it either today for the sake of time. So again, the idea behind our 3 and our 5 moving mean, the name comes from how many points we're taking the average from. So with the 3 moving average or the 3 moving mean, it's 3 because we're taking the average of 3 separate points to get the average value for our starting point, and then we do that all the way through our data so that we kind of get that effect of because we're taking all these averages, we're kind of in effect we're smoothing out the data. Think about it like we're ironing out the irregular fluctuations, we're removing them, we're trying to get rid of them. So we actually can't take the 3 mean smoothed value for January, because if we were going to do it for January, we'd need to take the point for January, the point before, and the point after. But we don't have a point before January, so we actually can't do January. So January is off the table. But we can do February by taking the value for February, the value for January, and the value for March, adding them together, 12, 8, 7, which gives us 27, which we divide it by 3, because that's a number of, the number of values that we've taken, and that gives us 9. So our 3 mean smoothed value for February is 9. And then we can find the value for March by getting the average of February, the average of March and April, adding them together, 8, 7, and 14, add them together, divide them by 3, just like with any other average, and we get 9.67. We can do the exact same all the way through. And we can also do the exact same with the 5 moving average. The main difference being that we actually lose our first 2 data points when we do a 5 moving average. And that's because, again, we don't have 2 points before January to use. We don't have 2 points before February to use. But when we're looking at March, we can take March. We can take the 2 points before and the 2 points after, divide them by 5, add it all together, and then we can actually get the smoothed value for March. And once we've done all of our smoothing, it can be a bit of a time-consuming process, and that's why it's usually kind of handy, kind of convenient, and nice and neat to kind of do it in a table or whatever kind of format works best for you. But once we have all of our values, we can actually plot our smoothed value on our time series plot as well. And that's actually super helpful because it actually makes it really, really clear like if there is like a trend or a pattern or a relationship that it has uncovered. And we've got a key here. So we can see that this here is our original data, and you can definitely start to see what I'm meaning by like irregular fluctuations. We've got all these crazy ups and downs. I actually can't really see if there's like a pattern or a trend there because it's just so up and down and obscured by these annoying like irregular fluctuations. So what we've done is we have applied smoothing, and you can see here we've got our 3-point and our 5-point. But because it's actually in black and white, it's kind of hard to tell like which is which. They look quite similar. We've got like our circle and our square. But another way that you can kind of tell the difference between them is by looking at how many points there is. Remember what I said before about how when we do the 3 moving mean, we actually lose the first point, which here is January, and the last point, which is December. So I can actually really easily tell, even without looking at my mean, that this must be my 3 moving mean smoothed data because I've lost my first and my last point, which means that this line here must be my 5 moving mean because I've lost my first 2 points and my last 2 points. So that's kind of the difference there. So we can start to, and as we look across at the different kind of lines, we can actually really clearly see the impact that our smoothing is having. You can actually kind of see that ironing out effect, that smoothing down. We're kind of ironing out the irregular fluctuations because we can see our 3-point mean smoothed line here. We can actually see that a lot of these crazy high irregular fluctuations have kind of really been, like we've said, been ironed out by taking those averages. And our 5-point line has been even further smoothed. Those really big variations have been even further ironed out. And if we have a really close look, we can actually start to see that maybe there almost is a bit of an underlying trend there. Because if we were to fit a trend line to our 5-point smoothed data, we actually might even start to see that maybe there is a little bit of an increasing trend there. Because now that we've got the effects of our irregular fluctuations moved out of the way, we can kind of start to see that a little bit more. So that's really interesting there. Again, we won't be touching on that. So that was removing the impact of irregular fluctuations. But if we want to remove the impact of seasonality, this is where deseasonalizing data comes in. And how we do that is with seasonal indices. So we won't focus on here too much because I would like to focus more on sequences. But the main things I'll draw your attention to is, again, that a season is any breakdown of time with equal periods in the year. So again, if we could do it month by month, in which case we'd have 12 seasons in the year. And seasonal indices, which are like the numbers that we use to deseasonalize and reseasonalize data. So these seasonal indices, what they're doing is they scale information to reveal trends without the influence of seasons. So if, for example, I had a time series plot where I plotted ice cream sales throughout the year, you'd definitely expect there to be a big spike in the summer months, and then in the cooler months, I probably wouldn't be selling so many ice creams. So if I wanted to know, is my business doing well because it's summer, or is my business doing well if we removed the impact of temperature from our data? That is where like deseasonalizing would come in. So that is, again, it's just removing the impact of seasonality. So yeah, like I said, we can see, is our business doing well because it's summer, or is our business doing well in spite of the fact that it's summer? So again, removing that impact of seasonality. And again, it makes our data more readable. So a seasonal index is usually a number around 1 because seasonal indexes are based around that average point being 1, and the sum of your seasonal indices will always equal the number of seasons. So if we're looking at days in a week, we'll have a seasonal index for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And the sum of all those numbers will add up to 7. And any of the points, any of the seasonal indexes that are below 0 means that it's a below average day, and anything below 1 is below average, and above 1 is above average. So for example, a seasonal index of 1.3 means that that season is 30% above average. So if I said, for example, if we were doing like ice cream sales throughout the year, and if the seasonal index for summer was 1.3, that'd mean the seasonal index, like that means ice cream sales in summer is 30% above average. So that's really important to keep in mind, that when we're interpreting seasonal indices, we're always coming back to what actually is the average. That's what we're coming back to. This is our formula to calculate the seasonal indices. So the seasonal index, so that number, that'll probably be around 1, a bit below, a bit above 1. Our seasonal index is equal to the value of the season. So for example, the number of ice creams sold in summer divided by the seasonal average. So that's, again, the seasonal average. You've got to calculate that before you can find your seasonal index. Again, a quick reminder that if you add your seasonal indices together, it will equal the number of seasons. So that can be helpful if you've got to find an unknown seasonal average as well. And again, if it's 0.87, that means that it's 13% below average. We're always coming back to the average. Like with any formula, it can be rearranged. So if we have our deseasonalized value, but we want to re-seasonalize the data to get back to the actual value, again, we can rearrange our formulas to do so. So I know I haven't spent too much time on that. We haven't gone in depth of how do we calculate seasonal indices. But again, that's definitely, I'd encourage you to do some practice questions on that and find some helpful videos and resources if you are wanting to do some extra study on that. And again, another little connection. If we did want to add a least squares regression line, like a trend line, to a time series plot, we definitely could do that to help kind of highlight those overall patterns and trends. So again, just making more of those connections. Awesome, we've done really well. We're already up to sequences. So if your brain needs a bit of a break, feel free to pause the video. But if you're happy to keep coming along for the ride, then let's get started on sequences. So sequences, we have our two types. Does anybody remember what our two types of sequences are? Hopefully it's thought of maybe something along the lines of arithmetic and geometric sequences. So sequences are a series of numbers that follow a pattern, unless it's a random sequence, which is kind of given away in the name, that it's a bit of a random sequence. But when we're talking about sequences, we're talking about a series of numbers that follow a pattern. So a sequence can be as simple as 2, 4, 6, 8, 10, 12. So we're following a pattern. All I'm doing is adding 2 each time. That's what I'm doing. And because it follows a pattern, we can actually predict the terms. So if we're given 2, 4, 6, 8, and I asked you to tell me what the next term would be, or the next few terms, you could probably tell me that the next few terms would be a 10, 12, 14, 16, and you could continue to apply that same rule of all I'm doing is adding another 2 because I can see that's the pattern, that's the rule that my sequence is following. So that's really interesting as well. And so to apply that in a bit more of a complex sense, all it comes down to is substitution into formulas, and some of which are on your formula sheet. So again, I just really want to emphasize to be super familiar with your formula sheet. So that you know what formulas you need to know, what formulas you don't need to know, and which formulas you need to know how to use. So again, go look up your formula sheet. Super helpful. A bit of sequence terminology. When we're talking about a term in a sequence, that's denoted Tn. So for example, T1, when n is equal to 1, T1, that's the first term in our sequence. If I was talking about T17, we're talking about the 17th term in the sequence. So, and each term, I covered that one. This is what I wanted to say here, and n always has to be a whole number. So if I said let n equal 1.5, so I can talk about term 1.5, we can't have that. It kind of just messes with the pattern, and we don't really do it that way when we're talking about sequences. So n always needs to be a whole number, and this is the example of the sequence I gave earlier. So this, all we've got to do is count along: term 1, term 2, term 3, term 4. Term 4 is 8. Super simple. This here, I missed that out there. But what I wanted to say there is that T1 is also known as A. So that's our starting point. So we can define that. Or sometimes it might be T0, but that's a little bit more depth than we'll be going into today. So A is another kind of way that we talk about our starting point. And our last little thing I'll draw your attention to is if we have like an ellipsis, like a dot, 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 that's just implying that the sequence goes on indefinitely. So arithmetic versus geometric sequences. This side of our Venn diagram is an arithmetic sequence, and this side of our Venn diagram is a geometric sequence. So let's have a look at the similarities and differences. First, the similarities, so what they share in common. Both sequences, I've cut myself off there. Both sequences have recursive definitions and general rules. So what's the difference between a recursive definition and a general rule? I'm so glad you asked. We're going to be talking about that. So this is the recursive definition for an arithmetic sequence. So the idea of recursion is we're taking one number and applying the rule to find the next term. Then we take that term, apply the rule to find the next term. We take that term, apply the rule, and we get the next term. And you get the picture. It can be a bit repetitive, but it's super helpful. We take term 1, we apply the rule, find term 2, then we find term 3, 4, and so on. So we have Tn plus 1 equals Tn plus D. So this is a recursive definition of an arithmetic sequence. So what we're saying here is Tn plus 1, the next term, is equal to Tn, the term we're talking about, plus the common difference. So this is our rule. This is what we're applying every single time. So in my example earlier, 2, 4, 6, 8, 10, term 1 was 2. We were starting at 2. You can have any starting point. A was 2. T1 or A was 2. And D, our common difference, was also positive 2 because we were adding 2 each time because I was adding the common difference every single time. And so that's how we've ended up with Tn plus 1 equals Tn plus D. And just to illustrate the substitution a little further, how this rule kind of works, if I was to say let n equal 1, then we'd have T1 plus 1 equals T1 plus D, common difference. So then we'd end up with T2 equals T1 plus D. So you can really see it coming out of what we're saying is the next term. To find the next term, all you've got to do is take the previous term and add the common difference. Whereas on our other side, our geometric sequences, we're not adding a common difference to find our next term. We're multiplying by a common ratio. So that's a really important distinction. So you can see here, I'll just pull up all our formulas. So you can see here, this is our recursive definition of a geometric sequence. We've got Tn plus 1 equals R, our common ratio, multiplied by Tn. So to find the next term, take the previous term or the current term we're looking at and multiply it by that factor, that common ratio, which is what we're multiplying it by every single time. This formula here is our general rule, or like our explicit definition of our arithmetic sequence. Because if, for example, I said find term 37, you're probably not going to want to use recursion to calculate all the way to term 37 because that would take up like your whole exam time and be super boring. You're probably going to want to find a way where you can skip straight to term 37, which is what you could do here. You could say let n equal 37, so then it'd be T1 plus 37 take 1 multiplied by whatever the common difference is, and then you're solving for Tn, which is term 37, and you'd be finding out what number is term 37 in the sequence. Coming over here, we've got our general rule for our geometric sequence. We have Tn equals A. Remember, A is the same as T1. It's like our starting point. A is T1, so that's our starting point, multiplied by R, which is our common ratio. And then we have n take 1. So, and because this is like to the power of n take 1, sometimes it can actually be a little tricky to solve for like the unknowns if you don't know what n is. So if you ever are trying to solve for n, it's probably best to just do it more by like trial and error and substitution. So what if we said let n equal 12 and you see if that kind of fulfills your rule? That might sound a little bit vague, but don't worry, I've got an explanation. I've got an example that'll help explain that further a little bit later. And then this here is how we find r. So it makes sense that if we take our next term and we multiply our common ratio by our previous term, then we get our next term. So it also therefore makes sense that if we want to find r, we can simply rearrange the formula and take the next term and divide it by the previous term to get our r value. And then we can do the exact same over here for arithmetic sequences. If we simply rearrange this formula to isolate d, we can also solve for our common difference. So again, our arithmetic sequence, we're adding a common difference each time. In our geometric sequence, we're multiplying by a common ratio each time. So another thing to keep in mind is that if your common difference is positive, or if your common ratio is greater than 1, the numbers in the sequence will get larger each time. And the bigger the common difference or the bigger the common ratio, the faster the growth. So it's an interesting thing. It's linear growth if you're talking about a common difference, but it's actually exponential growth if we're talking about a common ratio. So that's an interesting aside as well. And if d is negative, we're going to have linear decay. Or if r is less than 1, we're going to have exponential decay. So again, I just want to plant those thoughts in your mind to start you having a think about what that might mean. And we're going to revisit that in a minute. So sequences. Do you reckon, is this an arithmetic or a geometric sequence? What about this one? Arithmetic or geometric? So hopefully you might have been able to figure out that this is actually a geometric sequence and this one is our arithmetic sequence. And how you can kind of figure that out is because here we can see that we're adding the exact same number every single time. We're adding the exact same common difference to get to our next term. We're adding the same common difference to get to our next term, same common difference to get to our next term, same common difference to get to the next term, and you get the picture. We could go on forever, and it's going to follow this linear pattern. So here, to link with the previous slide, because we have a positive common difference, we're seeing that linear growth because it's following that straight line linear growth. But here is where we have an example of a geometric sequence that's been graphed. Because you can see we've got term 1, and then it gets a bit bigger, and then each time it's getting bigger and bigger and bigger because we're multiplying it by the same common ratio every time. And then when you multiply it by the same number again, and then multiply it by the same number again, it's going to follow this pattern. It's going to get bigger and bigger and bigger and bigger and bigger. So when we're graphing it, our line gets steeper and steeper and steeper, which is why we said before, this is our geometric sequence model, that exponential growth. And by exponential, we're saying it follows that exponential curve. So because here we have a positive R value, a positive common ratio, we are seeing that exponential growth. So that's a really interesting thing there. And to make a link, you might not be quite up to here in Unit 4 yet, but to link it to financial maths, which one of these would model simple interest and which one of these would model compound interest? It's interesting. Keep in mind that in simple interest, we're adding the exact same amount of interest every time, but in compound interest, we're multiplying by a common ratio each time. So that's an interesting link between how you can model a compound and simple interest using arithmetic and geometric sequences. So graphing, I already showed you a few graphs just before. Let me show you another one here. What else? Actually, I'll just quickly come back to this one. Let's show this one. if I pull out my laser pointer, you can see here that we've graphed n down the bottom and we've graphed Tn on the y-axis. And that is because we always graph n down the bottom. Sorry, let me skip forward again. And that is because Tn, so like the output, the number like that we're resulting in, depends on the term number. So term 1, term 2, term 3. So that's why we always graph n on the x-axis and we always graph Tn on the y-axis. It's kind of, again, it's like explanatory variable and response variable to kind of make that connection there. So here, what kind of sequence is this? Hopefully you've been able to identify that that's a geometric sequence because we're multiplying by a common ratio. And here we have an arithmetic sequence because we're adding the same common difference every time. So you can see here that, again, we're jumping up by 2 every time. We're following that consistent pattern. Whereas here, we're multiplying by 2 every time. And I've actually already graphed, I've color-coded it in blue. We can see that in our geometric sequence, we do get that exponential growth curve. Whereas if you follow the red dots that are going to be popping up on the screen, you can see that when we graph an arithmetic sequence, like that line there, we actually get that straight line, that linear growth or decay if it's negative. And that pattern is actually, that separation is only going to get further as we continue further on in our trend, because this is going to keep following that same straight line forever, but this is going to keep doubling and doubling and doubling and doubling and doubling and doubling. So it's so interesting to think about how they're modeled and represented differently, and it's especially obvious when we compare them on the same graph. So like I said, geometric sequences, we're thinking exponential curve, whereas our arithmetic sequences are linear. Another important thing, you can actually generate a sequence using your calculator, and that's again using recursion. So that's really important if you want to quickly answer a multiple choice question or if you want to check your work. So to make your calculator generate a sequence, you take your calculator, you enter your first term. So with our 2, 4, 6, 8, 10 example, our first term would be T1. So our first term would be 2. So you'd enter the number 2 in your calculator and then press equals and then enter your rule. So which would, in our case, would be +2. And then I would press equals, which would give me 4, which is term number 2. I'd press equals again and it would give me term number 3, which is 6. I'd press equals again and it would give me term number 4, which is 8. So you can see my calculator, by entering the number and doing nothing, pressing equals and then applying the rule, your calculator will realize that it wants you to generate a sequence, so it will follow in that pattern. So that's really interesting there. Okay, we're going to go through some practice questions. So question 28. A newly manufactured car is priced at $24,000. Each year, the car depreciates, that's a hint there, what might that refer to, by 25%. Write a recurrence relation to model this scenario. So I've got some questions off to the right here that I'd like you to think through. So first of all, is it arithmetic or geometric? And what tells you this? Again, how you approach a question, it might depend on whether it's multiple choice or short answer. And this one's a short answer one. You also need to work out, should I use recursion or the general rule? And here it said, write a recurrence relation. So we're going to use the recursive definition. And then another helpful thing to help you kind of step through a sequence type question is to always start with what you know. But here, we can see that a newly manufactured car is priced at $24,000. Each year the car depreciates by 25% and we're writing a recurrence relation. So this is what they've written here. They said T0 equals 24,000, our starting value, and then we've got Tn plus 1 equals 0.75 Tn. So hopefully from that you've been able to figure out that this is actually a geometric sequence because the car's depreciating by 25% each year. So we need to use a common ratio to model that. If it was depreciating by a fixed value, if it was depreciating by 500 every year, then we'd know to use an arithmetic sequence, because all we're doing is taking $500 off the value each year. And that's what we're doing again and again and again. But in this scenario, every year it's depreciating by 25%. So our R value, our common ratio, is 0.75. And that's to illustrate that after every year, every time after 1 year has passed, the car is now worth 75% of what it used to be worth, because it's dropped in value by 25%. And this is an interesting note here. I kind of alluded to this a bit earlier as well. Why am I saying T0 equals $24,000 when normally we start with T1? And that's because sometimes, this is where it gets quite tricky. Sometimes in word equations, depending on what we've defined our variables as, sometimes we actually start with T0. And that's because in this scenario, we've defined N as after every year that's passed. So T1 is actually, in this scenario, after 1 year has passed. But here we're told the initial brand new value is $24,000. After 1 year, when we're looking at T1, it's already depreciated by 25%. So it wouldn't be accurate to say that T1 is $24,000 because a year hasn't passed yet if it's still worth $24,000. And now let's calculate how much the car will be worth after 4 years to illustrate that. So we've got our formula, Tn plus 1 equals 0.75 times Tn. So what we're going to do first to illustrate that is we're going to say let n equal 0. So now we're going to have, if we say let n equal 0, we're going to have T0 plus 1 equals 0.75 times T0. And I know from up here that T0 is $24,000. And if I have T0 plus 1, I know that this is now T1. So by solving this out, I can now see that what we're saying is, okay, by substituting in n equals 0, let me say that at the start, let n equal 0, because that's what we've done here. By saying let n equal 0, we now know that T1, so term 1, so which is n equals 1, which is after 1 year has passed, our car is going to be worth 0.75, which is 25% less of what its previous value was. So our next, we have T1, like I've already said, equals 0.75 times T0. And because we know that T0 is the exact same as $24,000, because that's what equal means. Equal means like they're equal, they're balanced, they're the same. So T0, because we've seen T0, we can substitute that for $24,000. So what's 25% less of $24,000? Well, that's $18,000. So now we know that after 1 year of time has passed, our car has depreciated by 25%. Our car is depreciated by 25% after 1 year. We can now say that its new value is $18,000. Awesome. Now we're going to say let n equal 1. So by saying let n equal 1, now we have T2, term 2, is equal to 0.75 times T1. So now we have 0.75, not times 24,000 anymore, but actually times 18,000. Because after 2 years, it's going to be worth 25% less of what it was a year ago, not the original value, or it would just always stay at 18,000, which gives us 13,500. We apply the rule again, and now we've actually answered our question. So therefore, after 4 years, the car will be worth approximately $7,593.75. So that's our question there. Okay, awesome. Next question. The common difference for an arithmetic sequence is 16. Okay, so I already know we're talking about an arithmetic sequence, and I know we're talking about a common difference. And I know that it's positive 16. And I'm told that term 12 equals 236, but I'm not told the first term. So how do I find the first term? Well, I know I could work backwards using recursion. So I could put into my calculator 236 equals, and then subtract 16 and enter back until I calculated that I was back at term 1. But to do that a bit more mathematically and show my working, I'm going to use the general rule, which is the definition I have here. And I'm going to substitute in what I know, and then I'm going to work back to find out what T1 is. So I'm actually trying to solve in this question. What I want to find out is what is T1. So I'm going to define all my other variables. I'm going to say let n equal 12 because I know what term 12 is. I know it's 236. So that's actually another known value that I can substitute in to help me find n. So I'm going to say let Tn equals 236. I'm going to say let D, let the common difference be 16 because that's what we've been told. So now I can substitute in because Tn we've said is T12, so that's 236, is equal to T1 plus bracket 12 take 1 bracket 16. So now it's just a matter of solving and isolating T1. So I'm going to do 12 take 1 gives me 11. 11 by 16 gives me 176. And then to isolate T1, I subtract 176 from each side, which means that T1 is 60, which is awesome because I've already found term 1 now, which is really, really good. So that's how I would approach that question there. Okay, suppose that a savings account has $100 initially and receives simple interest at 5% per annum. How much would be in the account after 18 years? And then we can check our answer with our calculator. So we're not looking at financial maths yet. We're actually just looking at what are the applications of sequences to a simple interest scenario, which is lucky that I talked about a little bit about earlier about how I linked how arithmetic sequences can be used to model simple interest, because we're simply adding the same amount of interest every time. Whereas if we're looking at compound interest, that's a geometric sequence situation because we're multiplying by a common ratio each time, depending on whatever the annual rate of interest is. So I know that I'm looking for simple interest. But before I can start using my arithmetic sequence, I actually have to calculate how much interest they'd be receiving each year, which is kind of the only part of the question that's not like strictly sequence related. But because there's $100 in the account and the interest is 5%, all I've got to do is work out what 5% of $100 is. So by multiplying 100 by 0.05, I've got $5 more every year. So that's my common difference. That's how much is being added to the account every single year. So every single year, an extra $5 is being deposited into the account. So if Tn is the amount in the balance after n years, then T1 equals 105. Interesting, see what I've done here? I could have said T0 equals 100, and that's still equally as true, because again, now we're doing one of those practical application questions where our starting point before we actually do anything is what we want to have beforehand. So T0 after 0 applications of my rule is 100, because letting n equal 0, because here I've defined like Tn is the amount in the balance after n years, and because at T0, 0 years have passed, I know that there's $100 in the account initially, which means that T0 is 100, and then after 1 year has passed, there's $105 in the account. So I've defined that T1 as 105 so that I can use this rule here, because I can't use this rule with T0, I have to calculate T1. So that's what I've done there. And now what we're simply doing is substituting in our known values. I've now calculated T1. I know what D is, and I know that I want n to be 18 because I want to know how much is in the account after 18 years. So we substitute in. We're looking for term 18. So we do our math again. 18 take 1 is 17. 17 times 5 is 85. So now we have in essence, we have 105 plus 85, which if we break down, it actually makes sense how our rule is working, because this is after 1 year. So this is our original amount plus 1 year of simple interest. And this here, 17 times 5, that's saying, well, okay, what if I added $5 an extra 17 times? So that's how I've got my 18 years worth of interest. My $100 is my principal amount. This $5 is how much after 1 year. And then this amount is how much after an extra 17 years. Which gives us our final amount of $190, which again, you can double check using calculator recursion. So I'd encourage you to try that on your calculator now to make sure you've got the hang of that. So therefore, after 18 years, there'd be $190 in the account. Awesome. So we don't have too much time left, so I'm not going to go through this question here. But again, it is in the slides, so feel free to have a look at it. This question is about how many bacteria would be in a petri dish after a set amount of time. And just to briefly go over the approach to the question. So what they've done is they've defined all the variables, they've calculated R, they've come up with a formula that they can use. And now that they've got this formula, the goal is to find N. That's the goal, to find N. But like what I said earlier, it's actually quite tricky to find out what N is because we don't cover logarithms in general maths. We actually can't kind of isolate N because that's just like kind of tricky in maths. So what we do to solve a question like this is we actually use trial and error and substitution, which is a completely valid mathematical approach as long as we're showing out our working. So what they've done here is they've literally found N by using trial and error. So they said, okay, what if we let N equal 20? Oh, no, that's too low. That's not what we're looking for. They did a bunch more maths. They said, well, what about if we let N equal 100? Well, that's too high. That's not what we're looking for. What about 50? What about this? So pretty much they just tried all these different substitutions until they got the number they were looking for. Oh, I actually believe there could potentially be a bit of an error in these slides. I don't think those are the right numbers, but lucky I'm just going over the brief overview of the question, the structure and the format. But yeah, that's the essence of how they did that. They used it during doing substitution. And then alternatively, you could have also used recursion. So that's, for example, like doing on your calculator of just taking the first bit, multiplying it by 1.15, and then multiplying it by the common ratio again, multiplying it by the common ratio again, until you got all the way to term 78. So when we're trying to solve for n in these kind of trickier questions, you kind of have the two options of trial and error or recursion using your calculator. And whichever one kind of works best for the scenario is totally up to you. Yeah, sorry we briefly kind of went through that question. We haven't gone through the exam answer exactly. And yeah, I believe there might be some errors in these slides here potentially, but I just wanted to briefly overview the approach to the question. That was my focus. Which, amazing and not bad timing at all, brings us to Earth Geometry Part 4 of Unit 3, which is awesome. We've done really well to get through so much. So we're going to start a little bit by talking around like what is Earth Geometry, how does it kind of work? Because Earth Geometry is quite tricky to get your head around. It's very conceptual, like, hang on, I've got to kind of like picture the Earth as a sphere, and then like I'm trying to figure out like these different distances and like, oh my goodness, how does it even work? Like, this is just crazy. So we're going to try and break that down a little bit and hopefully make it a little bit clearer. So because the Earth is close to a sphere, hopefully that shouldn't be too much of a surprise for us, we can mathematically calculate, like the time zones, we can calculate distances between two different points on the Earth using kind of like the knowledge of what we know about the Earth being a sphere and what we know mathematically about Earth being a sphere. So when we're talking about Earth geometry, we're thinking latitude and longitude. So the first kind of definitions I want you to think about is great circles and small circles. See if you can recall what they are. So our great circles are a cross section of a sphere where the radius is equal to the sphere. So great circles are our largest possible circumference. So we're thinking like our biggest possible flat slice. So that's what we're thinking. Whereas our small circles are any circle with a radius less than that of a sphere. So let's pretend this model is Earth here. So have a look at this grey plane here. If this was the Earth, this would be our equator. That's our horizontal kind of line or ring around the Earth that we call our equator. So the equator is an example of a great circle because it's one of those biggest possible flat slices. And this red line here is actually also an example of like a great circle because it's a sphere. That flat slice can kind of be spun like any way around the sphere. But that's not really relevant when we're looking at like latitude and longitude, but that's just to illustrate like what a great circle is. When we're kind of coming back around to our small circles, like this blue line here, that's a small circle. We're thinking back to how it's any circle with a radius less than that of the sphere. We can kind of see that as soon as we move away from anywhere that would give us that largest possible circumference, we're kind of left with all of these smaller circles, which ironically and conveniently are called small circles, and I've color coded it there as well. So that's our great circles and our small circles. So let's move into latitude. So we've got our latitude and our longitude. So what they are is their coordinates. Latitude is a coordinate for the position of like how far north or south you are from the equator, and then longitude is how far east or west you are. So again, if we think about it like if this is our Earth, our latitude coordinate, which is like a number with like a degree sign at the end, our latitude is okay, how far north or south am I going? So if it's like up a bit north, okay, I'm coming up here, and then how far east or west is it? Or if it's like east, or if it's like west, or I might have that the wrong way around because I'm trying to do it the other way. But that's kind of the essence of what I'm trying to say. So if we're thinking about our latitude, we're looking for like an invisible kind of reference point somewhere on the Earth that's like how far north is it, how many degrees north is it, or how far south is it. And then once we come down south, we can kind of go east and west. So think about it like this. Think about it like grid paper. If you trace along grid paper, you can go, okay, I could go 5 squares up. Think about there being like almost invisible grid paper all over like the Earth, and you're tracing up. So, okay, it's this far up and then this far across. And then that's how you can kind of like pinpoint where the location is in terms of latitude and longitude. So the lines of latitude are actually mostly our small circle. So our lines of latitude are like, think about all of these like crazy amounts of like invisible small circles that are running parallel to the equator. And because they are where they are, they can measure how far north or south we are. So this, for example, by measuring from like the center of the Earth up to here, by measuring like this angle of elevation, we can see how far north this point is like from the equator. So lines of latitude are our small circles parallel to the equator, and the equator is also kind of like a line of latitude. So if we're talking about the only kind of like latitude circle that's a great circle, that's the equator. The rest of our latitudes are all our small circles. So again, latitude, we're thinking how far north or south. So latitude, always north and south. And the equator, again, only line of latitude, that's a great circle. And the latitude, like I said earlier, is the point of elevation or depression from the plane of the equator, again, which measures how far north or south you are. And lines of latitude are also sometimes called parallels of latitude. They're referring to the same thing. Okay, so I've just got my one illustration. So here we can see our diagram is Earth's front view showing parallels of latitude and the center of the Earth. So this, if we're looking at this as our Earth, this is our equator. So you can kind of start to see how we use our circles, or like our lines or our parallels of latitude to kind of get those coordinate points. So this, if I had a point like here on the Earth, it's at like 0 degrees latitude, it's on the equator. Whereas if I have a point that's down here, we can see that we measure that as 30 degrees south because our angle of depression is 30 degrees. So it's 30 degrees south of the equator. If I had a point that was up here, if I drew that in there, let me just make it nice and visual. So if I had a point that was here, that I was trying to figure out like what the latitude was, you can again draw that invisible line up from the equator, and we see that the angle of elevation, you can see here that it's 60. So that's 60 degrees north. So if I had a point here on the Earth that I was trying to like define in terms of latitude, I would say it's 60 degrees north. And like a point, so any point like on this latitude circle, oh, that's a terrible drawing. Let's just get rid of that. But anything, because the Earth is a sphere, it's 3D. We've got this line of latitude. Any point around the Earth that's on this 30-degree line is going to have a latitude value of 30 degrees south. So hopefully that makes a little bit of sense. And then on the other side of the coin, we have our longitude value. So lines of longitude are semi-great circles. Yeah, let me pull up my visual. Oh, it's on the next slide. That's okay, we'll go back. So these are our lines of longitude, and they're called semi-great circles because they're only half circles. So we've got this, and then there's a corresponding other half of the great circle on the other half, like of the Earth, but we're only really interested in like this side. So you can kind of see how all of our lines of longitude are semi-great circles. Have a look at that there. So lines of longitude are semi-great circles, referring to half a great circle, and they run between the north and south poles, like we saw in the previous slide. So they measure how far east or west you are from the prime meridian. So when we're talking about latitude, north and south, our kind of invisible reference point is actually the equator, but we don't have kind of like a vertical equator. So we've made up like this invisible point of reference that's called the prime meridian. So when we're talking about east or west in longitude, we're talking about how far east or west is a point from the prime meridian, which is our line of reference. And fun fact, that's like the 0 degrees longitude, and that line actually passes through Greenwich, England. So fun fact that might come in handy. And the lines of longitude are sometimes called meridians of longitude. So you might hear it referred to as like parallels of latitude and meridians of longitude. Again, just other names that we're using. And the international date line, which is 180 degrees, so it's opposite the prime meridian. So the prime meridian is our 0 degrees longitude, and the international date line is our 180 degrees longitude. And again, meridian, why they're sometimes called meridians of longitude, is because it's referring to that semi-great circle. So you can see here, like I said, this is like a front-on view of like the Earth. This is kind of a top-down view, so it might take your brain a second to wrap around like what we're looking at. But here we can see we've kind of got our prime meridian here, our 0 degrees. And then here, as we're moving right, you can see now we've gone 30 degrees east, 60 degrees east, 90 degrees east, 30 degrees west, 60 degrees west, 90 degrees west, until we wrap around all the way to the back, which is illustrated on this one over here, and that's our 180 degrees, which is our international date line. And then this is our prime meridian, our 0 degrees, which we can see here as well. And you can see there it crosses through Greenwich and England. So that's just to help out with your geography a little bit. So you can see that as we go around here, we go 30 degrees east, 60 degrees east, 90 degrees east, 120, 150 degrees east, and then back around at 180 is the back, which is kind of just like where east and west merge. So that hopefully will help illustrate that in your head a little bit more. So let's bring latitude and longitude together. And again, latitude and longitude is all like quite, it's quite complex. There's quite like a lot of like visualizing and that involved. So if you want to look up like some animated like visuals that might help you picture it a bit better, that's also something that could be really helpful. So again, coming back to my almost like invisible grid paper running all around the world. So lines of latitude and lines of longitude, they run across the globe so that every single location can be defined by their position on a line of latitude, which is how far north or south of the equator it is, and their position on a line of longitude, which is how far east or west it is of the prime meridian. So you can see here I've kind of drawn in some lines of latitude to illustrate that. So you can see that this might be like 70 degrees north, that might be 0 degrees because it's like right on the equator, that might be like 45 degrees south because again we're looking at those angles of elevation and depression. And again, that straight line that's just added on there, that's our prime meridian. That curved line there is like 30 degrees east. So you can see here that by looking at the intersection between, because I have this line of latitude that's an invisible small circle like running around the earth, and I also have this this meridian of longitude, this semi-great circle that's again like an invisible line running from the North Pole to the South Pole, you can actually really visually see here that they intersect. And that is literally where latitude and longitude intersect, which is how we get a coordinate. And this one, for example, I've said is about like 50 degrees north, whereas in reality that's probably more like 75 degrees north, and about 20 degrees east. So you can see how the the overlap between latitude and longitude is actually how we get our coordinates. So that's really cool to kind of be able to see that visually there. So again, by kind of seeing, okay, well, what is our angle of elevation? From there to there, I've said it's about 50 degrees. It's probably a bit more. And then how far east have we gone this way? We've said about 20 degrees away from the prime meridian. We've been able to pinpoint what the latitude and longitude is for that point. This is another really important thing to keep in mind. It's always latitude first and then longitude. So it's always going to be number, degrees, and then N or S, depending on whether it's north or south, or just 0 degrees if it's like on the equator. And then longitude, number, degrees, east or west, or like 0 or 180 if it's on the prime meridian or the international date line. But it's always latitude and then longitude. So how far north or south, how far east or west. How I remember the order of this is I think that like latitude comes first in alphabetical order. So I remember that latitude goes before longitude. So that's how I remember it. And also that latitude comes first alphabetically, which is what I just covered then. So again, degrees north or south, degrees east or west. And there's just a picture of the globe to illustrate that. So for example, the position of Brisbane, we've got lots of decimals here because it's really quite specific. Brisbane is at roughly 27.4705 degrees south and 153 degrees, 0.0260 degrees east. So we can see here our equator, our 0 degree latitude point of reference kind of is like about here. We can see that because Brisbane's kind of like down a little bit, we can see that we've kind of got that slight angle of like depression there. So that's why Brisbane's like 27 degrees south. And we also can see that it's 153 degrees east of the prime meridian. So it's actually coming a little bit closer to the international date line around like the back of the earth. So that's just an example there. Okay, awesome. These formulas here, straight from your formula sheet. Go check out your formula sheet. Again, that's my biggest advice. So we can see here that for Earth geometry, we're actually given two formulas to calculate distance. The D is referring to distance because here we're looking at the distance between 2 points. So, and the reason for that is we use the different formulas. We use this one when we're finding the distance between 2 points on the same longitude. And we use this one when we're finding the difference between 2 points on the same latitude. Now let me quickly illustrate why. Because when we have 2 points that are on the same longitude, so here and here, for example, we know that the difference that we're trying to calculate is that blue bit between my two red pointers. It's right there. That's the distance we're trying to calculate when we've got 2 points on the same longitude. But when we're trying to find the distance between 2 points on a small circle of like latitude, it would be, for example, the distance between the two red pointers now. It would be that distance there. But what I want to illustrate is that all of our great circles are the same size, which is actually quite important. So because I know that because again, the Earth is like pretty much a sphere, the distance between here and here, all I really need to do is figure out like what that distance there is, because all of our longitude lines kind of have that like same thing. Whereas if I was trying to find like the difference along this line of longitude, it would just be the difference between here and here. Because again, all of our lines of longitude are great circles or semi-great circles. But what I want to draw your attention to is that this parallel of latitude, or this line of latitude, and this line of latitude, because they're like vertical, they're at different horizontal differences at different horizontal points of the Earth, they actually have very different circumferences. So the difference between here and here is going to be very different between the difference of here and here. Because like these circles are very different sizes, whereas all of our lines of longitude are the same size. So that's actually like a bit of an obstacle that we run into, which is why, if we come forward again, that's why when they're on the same longitude, it's a bit of a simpler formula, because we know they're always going to be on like a semi-great circle, which makes the maths a little bit easier. But when they're on the same latitude, it's a bit more complicated, because we've got to take into account the angle as well, because we're like, well, theoretically, is our small circle, is it one of the smaller small circles? Is it a bigger small circle? So we've got to take into account that angle there as well. So that's just to illustrate that. So D, again, the distance between 2 points. Angular distance is sometimes referred to as AD, and the 111.2, we don't need to go into that like a lot, but essentially what that's saying is that for every degree we move, so for every degree that we move away from the equator, we're moving 111.2 kilometers away. So think like a clock arm. Because I just moved the clock arm 1 degree, that means the distance here has moved 111.2 kilometers. So just 1 degree in elevation from the equator means that we're moving 111.2 kilometers. So if I move 50 degrees in elevation, that means I need to do 50 times 111.2 to find out how far that we've actually moved, how far we have between those 2 points. And again, this is for when we have 2 points on the same line of longitude. So let's have a look at this, for example. If I wanted to find out what was the difference between this point here and this point here, I need to find out the angular distance, which is actually this distance in here. And so what I want to highlight is that why did we add the two numbers before to get the angular distance? So to get the angular distance here, again, I want to find out what this here is in degrees. And because this is 0 degrees, and this is, I know from like angle knowledge that this is 40 degrees elevation. So this is 40 degrees. And I know that this is 32 degrees. I know that if I add these two together, then that whole section in there is 72 degrees. So when our points are in different hemispheres, so when we've got 1 point up here in the north hemisphere and one in the south hemisphere, that's why we add the values together to get the angular distance, because it mathematically makes sense. We're trying to figure out what this distance is. But what about when we have this scenario here, when they're in the same hemisphere? Now we're only trying to figure out what this little value in here is. So I'm no longer interested in like the other hemisphere or how far it is from the equator. I'm only interested in finding out that here. And because I know that this is 18 degrees and I know that altogether this is 40 degrees, this in here must be the difference between 40 and 18 degrees. So by taking the bigger number, 40, and taking away the 18, I can actually get my angular distance is 22. So because I know that if this is 18 and this is 22, then that adds up to 40. So that's why when the points are in different hemispheres, that's why when the points are in the same hemisphere, we subtract to get the angular distance. So now that we've figured out what's the difference, what's the 111.2 and what's the angular distance, we can use it in our formula. But we'll do an example a bit later if we have time. So we're almost finished. We've got about 10 or so minutes left. So let's have a little bit of a talk about what we do when it's the same latitude, because I mentioned earlier that that's our bit more complicated formula. So to calculate the distance between 2 points on the same latitude, which is the same small circle, again, it gets a bit more complicated. Before, we knew that every great circle would be the same size. All of the meridians of longitude, they're all semi-great circles, which is awesome. But now we're looking at 2 points on the same latitude. So we use this formula here. And this time, this is an important distinction, the angular distance is the change in the longitude angle, whereas before we were looking at the change in latitude. And this symbol here is referring to the shared latitude. So the shared latitude, because if they're on the same latitude, they're going to have a shared latitude. So that is our angle. So let's use that example here. In this example that I've got here, I want to know the distance between my 2 green points. I can see they're on the same latitude. I can see that there. And they're both also on a meridian of longitude. And again, coming back to how we can find our angular distance. If both longitudes are east or both west, we subtract again to find the distance. If we have one of each, we add to find the angular distance. Then there's also kind of like the little trick of if it's above 180, we need to subtract the sum from 360, and that's how we find the shortest angular distance. That might be a little bit confusing, and if that is, that's okay, but that's pretty much to say once we go past 180, it's just shorter to go the other way. Why would you go like all the way around 270 degrees when you can just go, we'll scratch that. I'm not going the 270 degree way. I'm just going to take the shortcut and go 90 degrees. So that's why, that's like the little trick behind calculating the difference in the angular distance when we're looking at east and west. So here we can see that in our 2 points here, they're both on the same latitude, which is 12 degrees north. Again, real slick, 12 degrees north is going to be about here. So I'm sorry my example doesn't match my picture, but you can kind of like pretend that it does. So here we're looking at 12 degrees north. So that's our shared latitude, our theta value. And then now we need to find the angular distance between 140 degrees east and 130 degrees west. So to do that, we add them together, and like the example I gave before, they're 270 degrees apart. But because if we're already, that means that if we're going to go all the way around 270 degrees, that's actually not the shortest distance between the 2 points. It's way quicker to travel this quick distance here. So that's why we take the sum value away from 360 degrees, and that leaves us with 90. And then there's also that other way you can do it as well. So we're actually going to skip through time zones because we don't have time for that today. But again, please download the slides, go through this. The one point that I'll make here is true time is at the prime meridian. That's the real time. Because Australia is really far east, we're technically ahead of time. We're at about that plus 10 GMT, like we're like 10 hours ahead of true time. And that's because we're really far east. So I kind of find this helpful to picture it like a timeline. This is our true time. If we go east, we're moving like ahead in time. But if we're further west, we're kind of moving back in time. So when you're doing like time conversion questions, that's like really helpful to keep in mind, because you know that the one that's further east is always going to be the one that's ahead in time. That's just a breakdown there. The main thing to keep in mind here with time difference is that for every 1 degree, we're saying there's a 4-minute time change, because there's 15-degree time change every hour. But again, we're not focusing on that. Feel free to have a flick through these slides. So we're just going to go through one quick question before we move on to our tips and tricks before we finish up. So this question is, how far is the position 50 degrees south, 119 degrees east from the South Pole? So the interesting thing here is we're actually not given a coordinate, but because we're told it's the South Pole, we can actually work backwards and figure it out. So the South Pole has a latitude of 90 degrees south. And since our 2 points are both south, we subtract to find the angular distance. So the angular distance, because the South Pole, pretend this is the Earth, the South Pole is right up the top. So we've got am I silly? The South Pole is right down the bottom. So we have our equator, which is like our 0 degree latitude, and then we come down, we might have 30 degrees south, 60 degrees south, and then we have 90 degrees south. So our South Pole is right down the bottom. And this point here is at 50 degrees south. So we've got 1 point at 50 degrees south, 1 point at 90 degrees south. So again, our angular distance is 40 degrees, and because they're in the same hemisphere, we subtract to find our angular distance. And then because our points are on the same meridian, we use this formula here. We do the 111.2 multiplied by 40, which is our angular distance, which gives us our distance there. So that's just one quick example of a question. And note, we assume that like the South Pole and the North Pole lie on every meridian because they all meet at the top. So we don't need to worry about like, oh, is the South Pole at 119 degrees east? We just like assume that that's the case. Awesome. So now we have a few quick minutes left to just go through a few tips and tricks really, really briefly. So my first one would mainly just be preparation. Assessment year 12, it's all about the long game. I know it can be a lot. It can be super overwhelming, and it's like it's already April. Some of you might be feeling like you're in a really good study routine. Some of you might really be struggling, but I just want to encourage you that no matter where you're at, it's okay. And the first best time, like the best time to start studying was like, the start of the year, but the second best time is today. So even if you are feeling a bit overwhelmed, you're doing a really great job by being here and doing your best to stay on top of it all. So good work. You are doing better than you realize. For preparation, a few of my quick tips: come up with a study plan. For some people, that involves like a list of strengths and weaknesses. It might involve a bit of a timeline. It might involve thinking about when your external exams are, which is a bit closer to the date once you know when your externals are going to be. And also, like I said, get in good habits now. If you feel like, oh no, like I've already missed out, I haven't been studying properly, that's okay. Now is a great time to start. But if you have already been implementing all of those good habits, that's an awesome thing as well. My biggest thing as well is to stay on top of the content as you go, because otherwise you'll get to the external and you'll be trying to learn all of the content for the first time, and it'll just be so overwhelming and way too much to handle. Whereas if you stay on top of the content throughout the year, come the end of the year, you only need to revise it and review it, because your teacher's not going to be able to teach it to you all again right at the end of the year. So stay on top of the content throughout the year and make sure you're doing practice questions. You're finding out how do you study best, how do you work best, what's the most efficient way to study for you, and also to look after yourself. Having a healthy balance is really, really important. Again, it's the long game. And again, a few more hints and tips here as well. Use the resources available to you, like this today. 8R Notes has the books, the study guides, articles, free notes, the lectures. So make the most of all of that. If you have access to practice exams through school, make the most of those. Do those. Really, really stay on top of it. And again, linking back to what I said before about being organized, staying on top of things. For some people, that might look like a checklist of things they're going to study in an individual day. Some people have weekly planners. Some people have monthly planners. This is an example of my weekly schedule. I've got time set aside for work. I've got time set aside for my classes. I have time set aside for other important things like church and Bible studies, because I know I want to have time for those. They're a priority for me. So I know now that all of this time that I have left, well, yes, I may still have other events that come up. I know that that time is mostly time that I'll have available to study. So that's just one little example of how I kind of prepare for exams, but my system does not need to be your system. Find your system of organization, find your rhythm of study, and just works best for you. Again, it's the long game. Find the strategies, find the tips and the tricks that work best for you, and just make the most of it. And lastly, when you're actually in the external, my top tips, make the most of perusal, check your answers, start with the questions you feel most comfortable with, and then hopefully you'll just, maybe an idea will pop into your head about what you can do with the rest of them. Break it down, skip a question if you need to, and if you're like totally stuck, just write down everything you can think of, like get as much onto that paper as you possibly can. And if you're asked in a full sentence, answer in a sentence, because you never know what they're going to be giving you part marks for. So make the most of it. And then once you finish, celebrate your hard work, because year 12 is quite a journey. So that's actually all we have for today. Thank you so much for coming along, for joining us for this video, and I hope it's been really helpful and that you've been able to get a lot out of it. And yeah, I just really want to encourage you and wish you the best of luck in the rest of your studies. So thank you so much, everyone, and I hope you have a really good week. Bye.